dreaming, and the lamplight o'er him streaming throws his shadow on the floor, and my soul from out that shadow that lies floating on the floor shall be lifted nevermore.
This program is brought to you by Stanford University. Please visit us at stanford.edu.
And if you were to calculate the Gaussian curvature, remember in 2 dimensions the curvature is just it just has one component, only has one independent component, and it's the curvature scalar. If you were to calculate the curvature scalar, then on the outer rim of the torus here, you would find it's positive, and in the inner region here, you would find it's negative, and it is in such a way that the integral of the curvature over the torus is 0. Okay? And that's true for any object which has the topology of a torus. Here, I'm going to modify it. It's still a torus. We can modify it into a coffee cup or whatever. It's still a torus. What I've done is add some negative curvature over here and some positive curvature out here, but without changing the integral of the curvature. So there's a theorem about the integral of the curvature. The integral of the curvature is called the Euler number, and it's related to the number of holes and handles. On the other hand, if I put another hole in here, then I would change the integrated curvature, and this cannot be flattened. This has an integrated curvature which is negative, more negative than positive.
So let me repeat that here. So if you can't unfold a torus, a donut, so that it's flat, because if you give it a curvature 0.
Yeah. That doesn't prove you can unfold it. It just, here, the integrated curvature is not 0. And moreover, the integrated curvature is something which only depends on the topology. That's a theorem. That's Euler's theorem or Gauss's theorem. That the integrated curvature in here is equal to the integrated curvature for a sphere in certain units is +1. The integrated curvature for any torus is 0. The integrated curvature for a torus with 2 holes in it is -1. Integrated curvature with 3 holes, -2. And so it goes. The number of holes is called the Euler number. So the integrated curvature is related to the Euler number. I can't remember. Is the Euler number the integrated? Yeah, well, the Euler number is related to the number of holes and handles. And the integrated curvature only depends on the topology. It doesn't change if you put a bulge on it. It doesn't change if you put a bulge on the sphere, and so forth. Good. So here's what we know. The integrated curvature of this is 0. The integrated curvature of a plane is clearly 0 because its curvature is everywhere 0. And so this is the only one that would have any chance of being flattened. The integrated curvature of this cannot be flattened because it's always going to be -1. Yeah.
Is it possible to put a metric on the torus that's everywhere 0?
No. Everywhere 0.
I mean, in other words, make it flat. Not the.
Well, making the metric 0 doesn't make it flat.
Well, I mean, picking a metric.
Yeah.
Where the curvature.
Where the curvature is 0. Yes. 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 You can put a metric. That's the point. You can put a metric on a torus, which makes it everywhere flat.
Okay. Now, suppose I have a sphere, and I take one point out of the sphere.
That doesn't make a torus out of it.
I know, but can I make that everywhere flat? Can I choose a metric for the sphere minus a point, which would make it?
Can you choose? You're not going to choose the standard metric of the sphere. The question is, can you choose? Yes, you can. then a sphere less one point becomes the infinite plane. And the way to see that, in other words, it's a question, can you map a sphere to a plane? Can you map a sphere into a plane, or one-to-one correspondence of a sphere onto a plane? If you can, then you can just use the metric on the sphere that it inherits from the plane. Now, you can almost do that. There are many ways to do it, of course. You take the sphere, and you imagine that it's tangent to a plane. It's just sitting, it's resting on a plane, okay? You take every point on the sphere and you map it to a point on the plane by doing the following. You go to the North Pole, here's the North Pole, here's the South Pole, and you draw a straight line from the North Pole through the point in question, P over here, and you continue it until you hit the plane. Okay? Every point on the sphere gets mapped to a point in the plane in this way. The South Pole gets mapped right to the point where the sphere is resting. Every point gets mapped to a point on the plane except for one point, which is that? The North Pole. If you include the point at infinity, if you imagine one extra point, which is really the point at infinity, and of course it seems odd to think of infinity as a point. Infinity that way doesn't seem to be the same, but suppose you identify them all, then that's equivalent to the sphere. So here's what you can do. You can place a metric on the plane, the standard metric on the plane, dx squared plus dy squared, and say every pair of points, every pair of neighboring points has a certain distance between them as given by the simple-minded metric on the plane, and then map those 2 points to 2 points on the sphere. I don't think I did it very well, but simply give them the same distance as the 2 points on the plane had. In that way, you will have a metric which flattens the sphere. But this point at the North Pole here, since it corresponds to points very, very far away, this metric, the distance between this point, let's say this point and that point. What's the distance between that point and that point? It's going to be huge or infinite, right? This point maps out to infinity. This point over here next to it maps to some other place which is finite. So that means that the metric, the components of the metric up near the North Pole here are going to go to infinity. The components of this peculiar metric which flattens the sphere are going to diverge at the North Pole.
So an ant on the sphere, their measuring rods would shrink as they head to the North Pole, and when they measure triangles, they'd always get 180 degrees.
Yeah. Right. Well, if they made triangles by the rules of constructing geodesics, the rules of geodesics will no longer be great circles on here, or they may be, but if they are, they're actually they are.
Well, there must be some geodesics that are not great circles.
I think I have to think about it.
The question I had goes back to the drawing before you changed it. The two bagels come together. Is there any, just when I saw it, is there any meaning to that could be tied to two strings coming together and merging?
I'm sure we could find one if we tried hard enough. Offhand, I can't think of any.
Okay.
Yeah.
Yeah, is it possible to define a point transformation from like 2 space to 3 space?
Not a continuous one. Not a continuous one.
Because, you know, for example, if you
No.
2 space for a sphere, you know, the board, you can, it appears you can map that into a flat 3 space.
No. The sphere cannot be mapped. It depends on what you mean by map.
every point in a, you define a curvature with some kind of tensor, that defines a sphere. It's saying like what you're doing there, can you map that, not from 2 space, but into 3 space? Because again, it's embedded within a 3 space.
No, it's indifferent to, you can place a sphere and embed it in 3 space. That's not the same as mapping it. Well, mapping it onto, one-to-one. When I say mapping, I mean one-to-one correspondence. One-to-one, right. Every point in the three-dimensional space corresponds to a unique point on 2-dimensional space and vice versa. That is possible, but it's not possible to do in a continuous fashion. In fact, it's the only way you can do it is by scrambling up the points in a monstrously complicated way. So we could give you a rule for, here's a rule. 2-dimensional space is characterized by pairs of real numbers, right? Pairs of real numbers, we can write down the first real number, and let's take the region from 0 to 1, just for simplicity. So I take a 2-dimensional square, and I'm going to map a 2-dimensional square onto a 1-dimensional line. In each case, it's going to go from 0 to 1. Okay, can we do that? Can we really do that? Yes. Take the 2-dimensional point and characterize it by a real number. A real number means a decimal. 0.3794116, blah, 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 blah. If it's a rational number, then it's a repeating decimal. If it's an irrational number, it's a non-repeating decimal, and so forth. We need 2 of them. 0.846, blah, 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 blah. And now, take a new number that we're going to make out of them by intertwining the numbers here with the numbers here. So first we pick the 0.3. Then we go down to here, 8. Then we go up to here, 7. Then we go down to here, 4. Then we go up to 9. Then 6. You see what the pattern is. I've taken one from here, followed it by this, up to here, followed by that, and so forth. This is a unique number. Given a point here, there's a unique real number that you can make by this construction. And furthermore, given this real number here, I can take it apart and disassemble it, put the 3 up here, the 8 here, the 7 here, and so forth. So for every one of these, which means every pair of real numbers, there is, by this construction, a unique real number.
So long as you omit 0, right?
What's that?
So long as you omit the 0 point.
Why?
No, that's
Fine.
fine. 0 goes
You
to
could
0.
have a 0 point here. And it maps to the 0 point here.
Okay.
Right. But if you were to take a point like this and a close by point, let's take 2 numbers here which are close to each other. Let's see. No, I don't want these 2 numbers to be close to each other. I want to take pairs of real points. Here's one, and here's another one. And we take them to be close to each other. In general, they will not be close to each other on the line. So
it will be close because if their differences are out in the far ends, the changes in the image will be out of the far end too.
well, let's see.
But it won't be differentiable. I think that's what.
Yeah, well, it certainly won't be differentiable. Certainly will not be differentiable. No, I think it's always going to be very, very scrambled. There will always be points which are close together here, which are far from here. I think it's, say it again. 0.38.
You could take 0.1 and then 0.0 with a whole string of 9s.
Yeah.
Those are very
Right.
close.
So there's always going to be a lot of scrambling. You can't map it in any kind of continuous fashion. And so in particular, functions which are smooth on this plane here are going to be, if mapped to here, we take a function of x and y here, And we reconstruct from it a function on the line. How do we do it? Well, if we want to know what the value of the function is at point whatever it is, we reconstruct from this number here the real number, the pair of real numbers, go to that point, and take f and just bring it down to here. That function is going to be wildly varying. Neighboring values of x here will correspond to wildly, in general, divergent values of, not divergent in the sense of infinite.
It also depends on your starting point, whether you start with the 8 or 3.
Yeah, it does.
This is interesting.
Right.
I got a question about curvature. If you use
So needless to say, incidentally, we're not going to consider this a proper reasonable coordinate transformation.
if you're describing let's say space with geodesic coordinates, then the Christoffel tensor
Let me say exactly what that means. So not for your benefit, but for the rest of. I think by geodesic coordinates, we mean we have some curved space, and at some point, strictly at some point, we construct some geodesic like that. We construct a perpendicular geodesic like that. We call that the x and y axis, for example. And then any point, any nearby point close to this point over here, we can assign a coordinate, we can assign a pair of coordinates by dropping perpendicular geodesics to here and perpendicular geodesics to here, right? And then assign this point the coordinates equal to this distance and that distance. Is that what you mean by geodesic coordinates? Yeah.
I understand that the Christoffel symbols.
Yeah, those are the coordinates. Those are the coordinates in which the metric tensor at this point is delta ij, or delta mn, and in which the first derivatives of the metric are equal to 0. Okay? They're the coordinates which sort of match most closely to a flat coordinate system over here.
And so some of the terms of the Riemann tensor go away.
It's probably true. Some of them may.
Because they're just the products of the Christoffel symbols, but other terms of the Riemann tensor are
that's
derivatives.
Right. That's right. That's right. That's right. No, they won't go away. Oh, sorry. Yes, of course. In general, of course, they will go away. Yeah. The Christoffel symbols at this point are all 0.
Yeah, but they don't. But the derivatives with respect to.
Oh, I'm sorry. Sorry. The Christoffel symbols are 0. The derivatives of the Christoffel symbols will not be 0. But you're right. You're right. There are two terms, and the Riemann tensor has two kinds of terms. It has derivatives of the Christoffel symbols, and it will have plus quadratic things in the Christoffel symbols, just schematically. These, of course, will be 0. Why? Because at that point, only at this point, at that point, the Christoffel symbols will be 0. Why? Because the Christoffel symbols all contain derivatives of the g's. And if those are 0, these are 0. On the other hand, these things here will contain second derivatives of g. And those won't be 0.
And I was wondering if you get any insight into the Ricci tensor by looking at that particular case.
It's possible. I wouldn't be surprised. Good. So what you'd want to do is to relate both the Riemann tensor, the Ricci tensor, and the scalar curvature. You would want to relate it to the various second derivatives of the metric. So it's the second derivatives of the metric which come in. Very likely there is some picture that you can make from it from this construction. But it would involve the second derivatives of the metric. Now, what kind of nice geometric picture do you have about the second derivatives of the metric? Yeah, right. But nevertheless, it's correct that the Riemann tensor in those coordinates simply involves the collection of second derivatives of the metric. and that's it. Doesn't involve first derivatives, and so you can reconstruct it from those. And maybe vice versa also, that you could reconstruct this, or a lot of information about the second derivatives of the metric from the Riemann tensor. Okay, any other questions?
Special relativity.
Special relativity. Yeah, we're going to talk about that.
An example of, first of all, geodesic minimizes or maximizes the proper time for.
Yeah.
Okay.
Maximizing.
And you did an example where you have flat space, and actually for small b, you showed that if you maximize the path that maximizes the proper time is the path that minimizes the kinetic energy, which is or maximizes,
yes.
Minimizes the kinetic energy, which is Lagrangian.
Yes.
They showed those were equivalent. Can you do that in a more general sense?
Say it again?
Can you do, you showed that those two were equivalent, that the path?
Yeah, well, okay, but you have to understand that the kinetic energy is related to the path length with a negative sign. Right, okay, so it's not a crazy thing that minimizing one maximizes the other.
Can you do that in general if you just had a bunch of, say, a density of mass, no other forces, just gravitation, and show that the geodesic that you get is equivalent to minimizing Lagrangian?
Minimizing the Lagrangian for the point particle. Yeah, what you can't show, because it's not generally true, is that every geodesic is an absolute minimum of the distance. It's a local minimum. You know what the difference is?
Yeah, I know in a regular function the difference in local and global.
Yeah, right.
Maximum, minimum.
Okay.
If you just take any small variation, it's a minimum.
That's right. If you take any small variation, it's a minimum, but you may be able to find some large deviation which finds some path of,
So you get a whole collection.
yeah, you may have more than one geodesic connecting pairs of points in particular. In fact, as a rule, you do. In general, you do.
When
Yeah.
you see like a ring around the star.
Well, for example, but a simple example would be you take a nice symmetric hill in two-dimensional space. Let's make a very high hill. Now I'm not talking about space-time, I'm just talking about ordinary space, just to illustrate the point that there can be more than one geodesic. Typically, there will be a geodesic between here and here. Let's plot it horizontally, so I have a contour map for this thing. Here's the contour map for it. Big hill. Typically, there'll be a geodesic which it'll find a compromise. If I went all around here, that would cost me some path length in avoiding the hill. On the other hand, if I go right over the top of the hill, there's a great big distance around. So there typically will be a geodesic which will find a compromise and go somewhat up the hill, but not very far up the hill. Just think about taking a string, attaching it to here and here, and pulling it tight. All right? It'll climb partway up the hill. Okay. There'll also be another geodesic by symmetry which goes around the other way. I'm assuming these 2 points are symmetrically related to the hill over here. And in fact, there's even a third one. And the third one goes right through the center here, but it probably somehow is a local maximum of the distance. It's a geodesic by virtue of the fact that the tangent vector is covariantly constant. It is not a geodesic if what you meant was a minimum of the distance between 2 points. It happens to be a maximum. It has the peculiar property that if you had a string and you pulled it tight and you kept it perfectly symmetric, you would pull it right over the top of the hill and it would form, go right over the top of the hill, but if you displaced it a little bit, it would be unstable and it would slide off the top of the hill. So it's actually a maximum of the length. Local. What's that?
Only a local maximum. Because I can go like
Oh, yeah, of course. It's only a local, yes, it's a local maximum. But it is a geodesic. According to the official rules of geodesics, it's a geodesic, where the official rule means that the tangent vector is covariantly constant. So, good. Those good questions. Any more?
Such a thing as a stable and unstable geodesic?
Well, you can have a maximum or a minimum of the distance, yeah. If it's a maximum, then it's unstable. Yeah. What that means for the motion of a particle or something is another story, but
So what you did back then is you actually showed that you didn't even do the calculus of variations. You just took the proper time expression and you broke it up. Can you do that in more generality with just to say a mass distribution and show that you come up with a geodesic equation?
The geodesic equation will always be the equation that the tangent vector is covariantly constant. Okay. Now, what are you asking now?
I'm asking you got two calculus variations problems. One says minimize the Lagrangian, the other says maximize the proper time. And you show those were equivalent in special relativity with flat space and no other.
That's almost a definition. The question is, what's the definition of the action? Well, sorry, we compared variation of distance with variation of action.
Variation of action,
Yeah.
Variation of proper time, variation of action.
Well, that's just because, by definition, the action for a particle moving in space-time, by definition, is minus its mass times the tau, times the proper time. So that's essentially a definition. Right, and you can get the Lagrangian from this. We could do that. I mean, it doesn't take very long. It's pretty easy to do. Let's do it. Good, let's do it. And you can work out Lagrange's equations and show that they are the same as demanding that the covariant derivative of the tangent vector is 0. Okay, so the definition of the action along a trajectory is minus the mass times the proper time along the trajectory. And the proper time squared along a differential little piece of it here is d tau squared equals Gij, let's say, Gmn of position, won't bother writing what it is, dxm dxn. Good, all right. Now all we have to do is take the square root of this, that's d tau, and then integrate it to find the total path length from here to here. So the total path length is the integral. This is kind of a funny thing to see, an integral of a square root with a dx, but I'll make sense of it for you in a moment. Gmn dxm dxn minus m. That's the minus m which appears here. Right? That's the action. Now, what can I do to it to make it look more familiar? Pick one of the coordinates, a time coordinate. Let's pick time, x naught, and let's call it time. This is g mu nu, mu nu, mu nu, and so forth, okay? And let's write this whole thing out. It first of all has the space-like components. In other words, when mu and nu are both space-like. Then there's the mixed space-time components plus twice gm naught dxm dx naught. Why did I put a 2 there? Because it's symmetric. There's an equal one from gm naught and from g naught m. All right, so I just wrote it this way. Gm naught dxm dx naught. And then the last term is plus g naught naught dx naught dx naught. Now let's call dx naught, let's call it t. Let's call it x naught t. So this just becomes dt. Okay, now let's divide and multiply by dt squared, or by dt. Let's divide, multiply here by dt, and now divide this whole thing by dt. But if I do it inside the square root, that means dividing by dt squared, right? If I want to divide by dt, but then I want to put the dt into the square root, I make it dt squared. Okay, let's look at what we have. dxm by dt times dxn by dt. What is that? That's the product of velocities. This is the mth component of the velocity. This is the nth component of the velocity. Here we have 1 dt cancels, and we have dxm by dt. That's also a component, that's something linear in the velocity. And what about this here? What did I do here? Yeah, I forgot to call this dt squared. But I'm dividing it by dt squared, so this goes away. Well, now I have something that really looks like a Lagrangian. Here it is. It involves the positions. Remember, the g's depend on x. We have dependence on position and components of the velocity. It's a rather complicated Lagrangian. It's not like the good old non-relativistic Lagrangian, which only has 1/2 mx dot squared plus v of x. Everything occurs in the square root. That's a big nuisance, particularly when you start differentiating it. But you take this Lagrangian, which depends on the velocities and the coordinates, and you just do the Euler-Lagrange equations. And that will give you the equations of motion for the particle. It is also the same thing as minimizing, maximizing, making stationary the proper distance or the proper time, and would allow you to construct an energy function and so forth. So this is the Lagrangian for a point particle moving in an arbitrary gravitational field. Okay. You can take this, you can work out Lagrange's equations and prove that they are the same as, let's see what they're the same as. Okay, it's a little bit of a nuisance for the following reason. The equation for your geodesic in terms of the tangent vector has been d second x by ds squared, or d tau squared, plus, anybody remember what else there is? That's the equation for a geodesic. Now, the nuisance part of it is that this is going to give you an equation where the independent variable is going to be time. You're going to work this out, and you're going to write equations for x as a function of time. So the equations are going to be second-order equations, good old Euler-Lagrange equations, and they're going to involve things like dx by dt, whereas this is in terms of dx by d tau. So what you'll have to do is you have to convert everything to t notation instead of tau notation. So let's, for example, say this is a space-like component. Let's call it m, and the other ones stay the way they are. All right, the first thing we'd have to do is deal with this guy here. This is dx m by d tau, d by d tau. But we simply use the rule that differentiating with respect to tau is the same as differentiating with respect to t and then multiplying by dt d tau. But what is dt d tau? dt d tau is not 1. It's not 1. We have to remember what t is in terms of tau. T, and well, we have to work out what dt by d tau is. But we know what it is. All right, let's work it out. D tau squared is equal to g naught naught dt squared plus g naught 1 dx 1 squared, blah, 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 blah. And then we simply divide this by d tau squared, 1 d tau squared, d tau, same thing, sort of thing. And then we solve for dt by d tau. We just solve for dt by d tau. That tells us what dt by d tau is. And it's just some complicated thing involving the metric and the velocities. So something complicated but known goes in here for dt by d tau. And then we do the same thing again. D by d tau is d by dt times dt by d tau. Do the same thing here. Gamma dot dot dot, and instead of writing dx by ds, we write dx by dt, dt by, this is tau, sorry, tau. I'm getting myself mixed up. We just rework it so that it becomes an equation of motion for x as a function of time. It's easy to do, it's just elementary calculus, and it's the same equation as this. Let's not do it. It's more of a nuisance than anything. But the point is the logic. Logic is that the principle of least action and the principle of least proper time are the same thing in any metric. So if you plug in a metric, you'll automatically retrieve a Lagrangian for the motion of the particle. Notice this g naught naught here. Let's do a simple example. Let's suppose that only g naught naught was interesting. By interesting, it means different than the flat space metric. Let's suppose that g naught naught was different. What is g naught naught in flat space time? 1, right? 1. All right, let's simplify these by going to flat space time. Then what's gmn? Delta mn, right? No, gmn. Delta mn, or minus delta mn. All right, so this becomes essentially the xm dot dxm squared. I may have the sign wrong. We may need a minus sign. This one I'll take to be 0. In flat space time, gm naught is just 0. So let's forget this. And then we have g naught naught of x. Okay. Supposing that, have I missed anything? I did miss, what did I miss? I missed something. I think I missed the term which is dt by dt squared. Oh. No, that's here, right? Yeah, that's here. That's here. That's just 1. That's just 1, except I don't want to make that approximation. I want to let g naught naught vary. So let's let it vary a little bit. Let's let it vary and call it 1 plus something small. So let's call it delta g naught naught. All right, so this is close to the Newtonian approximation. The only thing that's not absolutely Newtonian, or the only thing that's not absolutely flat space here, is that g naught naught might depend on x. All right, now suppose the velocity is small. The velocity is small. How do you expand out something like this? How do you expand out? What do we have? We have square root of 1 plus something small. This is 1 plus something small. Right. It's 1 plus something small. And the something small consists of delta g naught naught and the square of the velocity. Okay? So what's the rule for 1 plus square root of 1 plus s? 1 plus s over 2. Okay, so let's work it out. First of all, we get minus m. I'm making a mess of this blackboard, but let's keep going. Minus m times, now it's 1 plus s over 2. Let's start with 1. And now plus s over 2. So what's s over 2? Plus delta G naught naught over 2 minus, let's just call it x dot squared over 2. That's this term over here. Okay? Do I have it all right? Okay. So the first term is just, why is it minus m? Oh, it is minus m. It's actually correct, minus m. The first term is minus m. Right? The next term is minus delta G naught naught over 2. And then plus mx dot squared over 2. What's this term? Well, that's very familiar. It's just mv squared, 1/2 mv squared. What's this term over here? This is not the energy, incidentally. This is the Lagrangian. The Lagrangian is related to the energy by changing the sign of the potential energy. These two are potential energies. These two don't depend on velocities, they're potential energies. So basically, yeah. M where? Oh, M here, right? Yeah. Okay, so in terms of energy, you would change the sign of these two. The first term, what would that be? In the energy. No, it doesn't matter, but what would it be? Yeah. It's the energy when the particle has no motion. And if I kept all the speeds of light, this would just be minus mc squared. Why minus mc squared? Because it's in the Lagrangian, not the energy. The energy, you change the sign here. What's this one over here? It's the potential energy, but now we remember something. We come back to something familiar, that the gravitational potential, normally we would have, I think it's minus the gravitational potential here. So minus m times the gravitational potential is just delta G naught naught over 2. Minus or plus? I think with a plus if I, no, I think with a minus if I remember. I always lose track of the sign. M with an M. So what do we find? We find the equation that says that the gravitational potential is just equal to delta G naught naught over 2. Now, why delta G naught naught? Do you remember earlier we identified G naught naught with G naught naught over 2 with phi? Do you remember that equation? Right. Why do I write delta G naught naught? Well, the point is that we don't really identify G naught naught with phi. We identify G naught naught with phi plus a constant. It was the derivatives of G naught naught that we identified with the derivatives of phi. So we can add a constant to G naught naught, and delta G naught naught just means the deviation from the constant. So this is just a good old equation that we had relating G naught naught to the gravitational potential. So, you know, you can work with these equations. It wasn't my goal in this class to spend a lot of time working with these equations, but just mainly showing you what they are. And of course, they're much harder than Newton's equations in the sense, not conceptually, but in the sense that whenever you have a square root to start differentiating, you're going to have trouble. So solving the equations is more difficult, but conceptually, it's just the same Euler-Lagrange equations that, okay, where were we? Let's get started. I did want tonight to study black holes a little bit, the black hole metric. Actually, this was a good starting point, but let's just go through the Schwarzschild black hole. Now, before we do that, it's very important to understand the concept of an accelerated reference frame in relativity. An accelerated reference frame is something which can have meaning in special relativity or in general relativity. And we begin with special relativity. In particular, the accelerated reference frame is simply the reference frame in ordinary special relativity as seen by an accelerated observer. Okay, but it's a little bit different. It's a little more subtle than it is in normal physics, normal Newtonian physics. All right, let's draw space-time. Here's space-time. Here's a light cone. Light travels on 45-degree axes. Time is vertically upward. X goes out of the blackboard this way. And Y and Z are only going along for the ride. We don't even need to think about them. They stick out of the blackboard, but we're not going to play very much with them. All right, now, if you remember, an accelerated reference frame in Newtonian mechanics is one whose coordinates are curved, and they're parabolas. They're parabolas, all of which are sort of parallel to each other, and they just correspond to the acceleration of the motion of an observer at rest in the moving frame. So at rest in the moving frame means moving along one of these lines. And that observer is an accelerated observer. Right? Notice one point, well, that is what an accelerated observer is. The acceleration is uniform. We assume the acceleration is uniform. And that means at any given time, if that observer measures his own acceleration, and you can measure acceleration, you can feel acceleration. Acceleration has an uncomfortable effect. The acceleration all along here is constant, so that poor observer who is being accelerated with 25 Gs of acceleration is uncomfortable, but equally uncomfortable at all times, including times at which he's coming in from far away. All right, what kind of observer in special relativity corresponds to a uniformly accelerated observer? It's one who feels the same amount of acceleration at all times. You might think, again, that that's a parabola. In other words, x equals, let's say, constant x naught plus acceleration times t squared. Acceleration over 2 times t squared. Well, that's going to quickly make that observer move faster than the speed of light. Remember, with a uniform acceleration, velocity is equal to acceleration times time. So if you wait long enough, you'll be moving with faster than the speed of light. That can't be what a real accelerated reference frame is. Anybody moving faster than the speed of light feels something very, very different than what we feel, and I don't know what it is. Okay, so that can't be the right idea. The right idea is a hyperbola. I'll explain why in a minute. An observer moving along a hyperbola in special relativity is a uniformly accelerated reference frame. Now, you can take that hyperbola to be the hyperbola x squared minus t squared is equal to a constant. X squared minus t squared equals a constant is a hyperbola. And it's a hyperbola of radius, let's call it c squared. It's a hyperbola of radius c. In other words, the distance from the origin here at closest approach. This is at closest approach, the distance of the hyperbola is c. Now, a hyperbola like this is Lorentz invariant. That means if you do a Lorentz transformation, the hyperbola goes into itself. How do I know that? I know that because x squared minus t squared is an invariant of a Lorentz transformation. We've gone through this several times. X squared minus t squared is the thing which doesn't change when you do a Lorentz transformation. In other words, if I do a Lorentz transformation and I have a point at which x squared minus t squared equals c squared, if I Lorentz transform it, after the Lorentz transform, it will still be on the same hyperboloid. The mathematics of this is almost the same as saying you have a circle, which would be x squared plus y squared equals a constant, and saying that a rotation preserves the circle. A rotation about the origin preserves the circle. In the same way, if you do a Lorentz transformation, this curve will simply slide into itself. Right? That curve is Lorentz invariant. And that means what's going on at this point over here is, as far as the observer moving along here, is exactly the same as what's going on over here. He feels the same thing here as he feels here, as he feels here, and so forth. The mathematics is very similar to saying that somebody going in a circle would feel the same thing here as here, as here, as here, as here. There's a symmetry to the problem. And the symmetry is such that somebody traveling along this trajectory will feel a constant influence of the acceleration at all times. Okay. That's the idea of a uniformly accelerated object in special relativity. Now, does it ever exceed the speed of light? What are the asymptotes of this hyperbola? It's asymptotic. Its asymptotes are simply the light cones. It never gets up to the light cone. It never exceeds the speed of light. It just asymptotically gets closer and closer to the speed of light. Okay. That's what a uniformly accelerated object is in special relativity. Something which is approaching the speed of light with uniform proper acceleration. Proper acceleration means the acceleration in the observer's rest frame. As the observer is being accelerated, that observer, in his own frame of reference, senses always identical acceleration, point by point, as he moves along. Very, very much like an observer moving in a circle would experience the same acceleration moving around in a circle. Okay? So this is what is called a uniformly accelerated object. A uniformly accelerated reference frame is really just you start at t equals 0. Here's t equals 0. And you mark off a bunch of meter sticks. And then you let each meter stick, whoops, I didn't draw that very well, move on its own hyperboloid, on its own hyperbola. And that becomes a uniformly accelerated reference frame. But what that means, if this hyperbola here is x squared minus t squared equals c squared, let's call it 1. Let's say this is 1 meter. The 1 meter stick, the end of the 1 meter stick is at x squared minus t squared equals 1. What about the 2 meter stick? What's its equation? X squared minus t squared equals, what do you want to write? 4. 2 squared. X squared minus t squared equals 9, and so forth. Okay? That's a uniformly accelerated family, a family of uniformly accelerated ends of meter sticks. Now, what about time? Time along these meter sticks ticks off along here, and it corresponds, this is a definition of time is to do the same kind of Lorentz transformation on this line here to move the line forward from one time to the next time along each of these hyperboloids. That would look like this. Here would be time. Remember, when you do a Lorentz transformation, the surface of constant time, the surface of simultaneity, what an observer calls simultaneous, gets tilted. So what we're doing is we're making a series of Lorentz transformations along this trajectory to make them go faster and faster and faster and faster. And the surface of simultaneity is getting more and more tilted. Oh, I'll write the equations for these things in a moment. But this is what a uniformly accelerated reference, this is the closest thing that there is to a uniformly accelerated reference frame. Each one of these observers sees something going on which is time independent. It sure looks like it's time dependent, it looks like it's going faster over here, but what they feel in their own rest frame is identical all along the trajectory. But does this one feel the same as this one, as the same as this one, as the same as this one? No. You can see that from the circle analogy. From the circle analogy, imagine a family of observers moving in circular orbits, all attached to the same rigid rods here. Would these observers all see the same acceleration? No. Who gets the biggest acceleration?
One on the outside.
One on the inside. You make a tight turn, and it's a bigger acceleration. Am I right? Did I get it right? Yeah.
Right, they're more flat on the outside, they're curved on the inside.
Yeah. Right. More curved on the inside here than the outside. Okay, actually the right thing to be thinking about is uniform velocity, not if it was the same velocity. They all have the same velocity. That's the appropriate analogy. Not that they're attached to sticks this way. Yeah, they all have the same velocity. They all move with the same velocity. That corresponds to the, well, okay, that's the right thing to do. All right, these observers see different accelerations, not with time, but with where they are along here. In fact, the deeper in you go, the larger the acceleration of these observers. The acceleration, in fact, is basically 1 over the distance from the origin. 1 over the proper distance from the origin is the acceleration. That's the closest thing that there is in special relativity to the concept of a uniformly accelerated reference frame. You might ask, why not just take one of these uniformly accelerated guys, which is a hyperbola, and then take another hyperbola displaced from it by a given distance, so that each one is sort of parallel to the other and they all experience the same acceleration. What would happen? This would be a very odd coordinate system. The reason being the distance between each neighboring observer would change with time. Why is that? Because things are, in my frame of reference, standing here, I've kept the distance fixed. This distance is the same as this distance, is the same as this distance. But what happens in the reference frames which are accelerating? In the reference frames which are accelerating, the moving observers see these points get further and further apart. So that's not a good definition of an accelerated reference frame. This is the best that you can do. All right? And notice that it has the feature as you get closer and closer to the center here, the acceleration goes up and up and up. Another way to say it is that people moving on these trajectories experience effective gravitational fields. Why? Because acceleration and gravity have the same effect on things. So if we had an elevator over here that was being accelerated this way, and another one over here being accelerated this way, and another one being over here accelerated this way, they would experience different gravitational fields, larger and larger and larger, until you got to the observer who was at such a small distance here that they have an enormous acceleration as they go around this bend. As they go around this bend in space-time, there's an enormous acceleration, in a very small amount of time, proper time, from here to here, the velocity has changed a great deal. Get even closer, and in an even smaller distance, the velocity changes a lot. Smaller amount of time. So these ones are the ones that are maximally accelerated. These ones out here have a very negligible acceleration.
That's a constant acceleration.
Constant along the trajectory, but not constant from observer to observer. So effectively, what we have here is a series of people in this reference frame, a series of people separated by fixed distances, but each one, as you go down the line, feeling a stronger and stronger gravitational field. The one in here is experiencing an enormous gravitational field because he's so highly accelerated. The one out here experiences a very negligible gravitational field. Or you can think of it as a sequence of elevators, where the elevator lowers down very close to here, is experiencing a very large acceleration. The elevator up high is accelerating with a small acceleration. And so in this kind of geometry, in special relativity, there really is no such thing as a uniform gravitational field. The effective gravitational field, from the equivalence principle, the effective gravitational field for a uniformly accelerated observer becomes infinite at that point. Now, there's nothing happening there, nothing special happening there. This is flat space-time. It's just that we're accelerating these observers. Somebody is giving them rocket ships or doing something to accelerate these observers. Maybe in this picture, of course, x corresponds to the vertical direction of space. T, being the vertical direction of space-time, is not the direction that elevators move in. These elevators are moving horizontally, so that's the vertical direction. What happens, supposing this observer who is being accelerated, he's being accelerated, a rope is pulling him, okay? A rope is pulling him and causing him to accelerate, or a rocket is accelerating him. Some thrust is causing him to accelerate and move down this trajectory. What happens if this observer, out of his rocket ship, drops a rock or anything else? What does that rock do? It is not connected to the accelerating device. It's not connected to the rockets. It's not connected to the cables that are pulling the, what does it do? It moves in a straight line. It moves in a straight line. Right. It's going down from one hyperboloid to the next. And eventually passes through that point over there. So when he throws this rock out of the rocket ship, let's say he just drops it, doesn't throw it, just drops it. So the rock is moving with the same velocity as the spaceship over here. Just drops the rock out. But of course, the rock is not being accelerated. So the spaceship is being accelerated away from the rock. But from the observer's point of view, the rock is falling. Where's it falling toward? It's falling from one hyperbola to the next hyperbola to the next. And so it's falling down. It's falling down into this region of enormously large acceleration. Is it getting accelerated? No. But does it look like it's getting accelerated relative to these observers? Sure. So this object, what's that?
It also takes forever.
Well, we're going to see that it takes forever. Yes, we're going to see it takes forever. Well, we have to define these time sections correctly. Okay. But before we do, we can get a general picture of what's going on. Now, there's one other thing which is kind of interesting. Think of all these observers. Think of this rock passing here. This is a very special kind of rock. It's a musical rock. Well, maybe, and it's a special kind of music. It's carried by light waves instead of sound waves. All right, so it's flashing music and sending out light rays. The observer over here, let's draw him more clearly. Let's get rid of this rock over here. This rock, which falls through over here, the musical rock over here, sends out light rays. and this observer over here experiences them. Okay? But once he has passed through this point here, this light cone here, no signal that he ever sends will ever get to this observer. No signal from here will ever get out past this light cone. That's the restriction, that nothing moves faster than the speed of light. So any signal that this rock sends will never get out to the observers out here. This geometry has what is called, or this geometry or this coordinate system has what is called an event horizon. Now, there's no black hole around. There's not even anything gravitating. There's just a uniformly accelerated coordinate system, musical rocks which fall through the light cone here because they move in straight lines. But from outside, once that rock has passed, once the musical rock has passed the light cone, or the light-like surface here, it's gone. It's gone. It cannot report any activity beyond that point.
It might help to notice that the rock actually isn't moving. The only thing that's happening is the time is elapsing on the rock.
Well, it might be moving, but it also might be not moving. Yeah, that's correct. It wouldn't be moving in the stationary reference frame. Yeah, let's draw that more accurately. That's correct. It's not. If it happened to be let off the ship at exactly this point here where the hyperboloid was vertical, it would just move up straight. And in our reference frame where we're drawing this picture, the rock would be standing still. Okay? And it might be emitting signals. Those signals would go up. But once it passes this point, it can no longer send any signal to what I'll think of as the outside world now. We'll think of this as the outside world, and we'll think of this as some place behind an event horizon.
Question?
Yeah.
At this point, is the origin there, is that arbitrary? Or
Is what?
Is the origin...
Yeah, the origin, but right. But I'm thinking of these as real material observers. Not just a coordinate frame for a moment, but real material observers connected by meter sticks, watching what's going on. The origin is, right. Well, of course, this observer over here could always decide at some moment to disconnect himself from the accelerating device and just fall through and make contact with this. That's fine. But no observer who stays on the outside, no observer who makes sure that he stays to the right of this light cone, who doesn't allow himself to fall through that light cone, can ever get a signal from behind here. So that's the, yeah.
Wouldn't the rock move in a path that's sort of tangent to the hyperbola?
Over here.
Since it has a increasing x with time?
If it was dropped off right at this time, okay, let's see. If it was dropped off later, yes, it would move this way. Yes, but it would still pass this light cone because it's moving slower than the speed of light. Yeah. So at some point, it would pass this point of no return, shall we call it.
The rock can still get signals from the observer?
Yes, the rock can still get signals from the outside. Right, the rock can get signals from the outside. Right, so the horizon is a kind of one-way door, or one-way membrane, I don't know what to call it, one-way filter. One-way
mirror.
One-way what?
Mirror.
One-way, well, no, it's not a mirror. I don't think it's a mirror to anybody. Nobody sees anything reflected off it. It's just a one-way, that's all. A one-way door, a doorway to, okay. Now, let's actually write some coordinates. I'm going to actually tell you in detail what the coordinate transformation is. Was there a question? From the ordinary reference frame to the uniformly accelerated one. Questions? No questions. Good. Is it clear what's going on in that picture? I think it's pretty clear. And this is kind of the quintessential example of a horizon. And one of the interesting things that you can see about the horizon is that for somebody who falls through it, nothing special happens. It's just a non-event. Whereas from the person from the outside, they're seeing something rather peculiar, and we'll try to figure out what it is that they see peculiar as the rock rides on its trajectory. Okay, let's go back to circles for a minute. Here's circles. Here's x, and instead of calling this t, I'll call it y. But notice that y is a great deal like time here. All right. What is the coordinate transformation from polar coordinates to, or from x and y to polar coordinates? That's the relationship, in fact, between the accelerated reference frame and the ordinary reference frame. The ordinary reference frame is like x and y, and the accelerated reference frame is more like polar coordinates. Okay? So the polar coordinates here are r and theta. Theta is angle, and it sweeps you along a circle. As theta varies, keeping r fixed, you stay on a circle, but you sweep along it. That sounds awfully much like staying on a hyperbola and sweeping along it. So theta must be something like time along this trajectory here, because it varies along the circle, but doesn't vary as you go in and out. Okay. What's the connection between x, y, r, and theta? I think we've done this more than once. X is r cosine theta, and y is r sine theta. And notice that x squared plus y squared equals r squared. That's because cosine squared plus sine squared equals 1. Okay? What's the relationship over here? The relationship is almost identical, except that you replace sines and cosines with hyperbolic angles. Now, do we all know what hyperbolic sines and cosines are? Yeah. We do, don't we? Because we've learned it before.
We learned it in the fall.
We learned it in the fall. Good. So at least some of us who remember. All right, the answer is x equals, we can use the coordinate r again, and r just tells us which one of these hyperboloids we're on. It tells us how, at the moment of closest approach over here, it tells us how far we are from the origin. That's the same r as appears over here. But instead of theta, I'm not going to call it theta. I'm going to give it another name. I'm going to call it omega, and I'm going to write r hyperbolic cosine of omega, and y equals r sinh omega. Omega is the thing which varies along here. Let's see what it is at this point over here. As r equals 1, what is, and let's call this now omega equals 0. This is omega equals 1. This would be omega equals 2, and so forth. This would be omega equals minus 1. And omega is the thing which the observer along here experiences as a kind of time. It varies from here to here to here to here. It varies from here to here to here to here. Hyperbolic cosine, what does hyperbolic cosine range over? From what to what? Or what does omega range over? Minus infinity to plus infinity. Hyperbolic angles are not like ordinary angles. They don't go from 0 to 2 pi and come back to themselves. They vary from omega equals minus infinity way down here. So this observer coming in from a long way off starts at omega equals minus infinity, comes up, and then goes back out, and eventually is omega plus infinity. So omega equals plus infinity is way, way out here on the ends of the hyperboloids, the asymptotes of the hyperboloid. Omega equals 0 is over here. And this is the coordinate transformation to hyperbolic, to accelerated coordinate system. I don't call this t. It is the time that the accelerated coordinate observer will use. Okay? I don't call it t because we've already called t something else. So omega is a kind of time. Notice that it does vary in a time-like direction. It doesn't vary as you move horizontally. It moves, at least over here, varies as you move vertically. Okay, that's the...
Why is that y instead of t?
Sorry, t. My mistake, t. T. My mistake. Okay. Right. That's the coordinate transformation. And what about the other two coordinates of space? Z and y. Different y, not that y. Just the other two coordinates of space, y and z. What do we do with them? Nothing. That has to do with the fact that if you're Lorentz transformed along a given direction, the perpendicular coordinates don't change. All right, so as this fellow is being accelerated, and he has meter sticks oriented in the direction perpendicular to the acceleration, nothing happens to them. Okay, so y and z, nothing happens to. That's the uniformly accelerated reference frame. And this is the event horizon for the uniformly accelerated reference frame. What else do we have to say about this? I wanted to say something else about this. Oh, yeah. Let's work out the metric of flat space. Now, we're talking about flat space. All right, this is flat space time. But I want to write its metric in terms of r and cosh omega. Okay? We can do this in a number of ways. Let's just brute force it. What is dx? Dx is equal to dr times cosh omega plus r times the derivative of cosh omega, which is sinh omega, times d omega. All I've done here was write that the differential of a product is the differential of the first factor times the second, plus the second factor times the differential of the first, and the differential of cosh omega is sinh omega d omega. What about dt? dt is equal to dr sinh omega plus r cosh omega d omega. I've used the fact that the differential of sinh omega is cosh omega. Okay. Now let's calculate the metric. We know what the metric is. The metric is dt squared minus dx squared, right? Flat space time. I'm not even going to worry about y and z. They just go along for the ride. So let's write down the metric. d tau squared equals dt squared minus dx squared. Okay, let's see what we get. From dt squared, we're going to get a dr squared. So first of all, we'll get a dr squared. But then from dx squared, we'll also get a dr squared term. And what are we going to get? We're going to get dr squared times, let's see, I got to be careful here, or I'll get the, yeah, I got to keep my negative sign straight. dt squared, d tau squared equals dt squared. Yeah, no, we're okay. Okay, so good. So what do I get from the two terms with the dr squared? We'll get sinh squared minus cosh squared, right? Sinh squared minus cosh squared. What's sinh squared minus cos squared? Sure it's not minus 1? I think it's minus 1. So we get the r squared with a minus sign. Now we're going to get another term with a d omega squared. That one's going to have cos squared minus sinh squared. There's an r here. Cos squared minus sinh squared. What's cos squared minus sinh squared? 1. But we're also going to have an r squared. So there's going to be plus r squared d omega squared. And then there's going to be some other terms. There's going to be a term, for example, from dt squared here. We'll have a term with dr times d omega, a cross term in the metric. But let's look at it. What's it going to have? It's going to have sinh omega cos omega times r. Well, there's going to be a cross term from here, cos omega sinh omega times r. The two cross terms are the same, except that we're subtracting dt squared from dx squared. The result is they cancel. There are no cross terms. This is the metric. This is the metric of flat space-time in uniformly accelerated coordinate system. Now, the uniformly accelerated coordinate system should be thought of as only covering the part out here. Doesn't cover the region in here. We can make it cover the region in here, but think of it as r greater than 0. This is the metric, and it's the metric that describes everything in this uniform accelerated reference frame here. It's flat space-time. It's just flat space-time. But notice what it has. It has g naught naught equals 1, and it has g r equal to r squared. Incidentally, the other components of the minus r squared? Sorry, do I? But just yeah. G omega omega equals 1. GRR equals minus, no, r squared. And GRR equals minus 1. This is kind of an interesting metric here. G omega omega is like the time component of the metric. Notice that it varies like r squared. It varies, and remember that g naught naught is very much like the Newtonian potential. We have a Newtonian potential which is growing as we move out in r. That's the reason that things fall toward the origin. They fall towards the origin because the time component of the metric, which is like the gravitational potential, is increasing as we go away from the origin. So in this accelerated coordinate system, where g naught naught is not just equal to 1, but where it varies with distance, there's an effective force on an object which is pushing it toward r equals 0. All right, so that's everything there is to know, I think, about the uniformly accelerated coordinate system. There's another name for this region of space-time over here when it's described in terms of these coordinates. It's called Rindler space. Rindler space. I don't know why it's called Rindler space. I presume Rindler was the first one to, he's certainly not the first one to have studied it, but his name got attached to it. He did something, I'm not sure what, but that's the uniform acceleration coordinate system. And Rindler space has a horizon. That's what makes it interesting.
I have read that this Rindler quadrant for uniformly accelerated reference frames are a subset of Minkowski space.
Well, it's obviously a subset of Minkowski space. It's a quadrant of it. Yeah.
What does the geodesic look like?
in this accelerated?
Well, that's okay, good. First of all, what does it look like all right, here's a geodesic. Okay. What does it look like in R and omega? Well, R equals 0 is not just a point over here. R equals 0, R very, very tiny. R very tiny is this whole hyperboloid, which is very close to the light cone. The whole light cone can be thought of as R equals 0, or it's an extension of R equals 0. All right, so what happens is the particle pops out of R equals 0. Let's plot its motion, or let's draw its motion. There. Now let's plot omega and R. Omega and R, these are the coordinates in the accelerated reference frame. Okay, so let's start at omega equals, this is omega equals minus infinity. Omega way, way down here is omega equals minus infinity, which means from this point of view, the very remote past, these incoming asymptotic hyperbolas, the particle comes in, crosses R equals 0. So long in the past, it's at R equals 0. It pops out and goes all the ways out to R equals, let's say, 1. It pops out, goes to R equals 1, turns around, and falls back in. That's what happens over here. It's gone from the remote past to the remote future, jumped out in the remote past, gone through some maximum R. In other words, it's in a gravitational field. There's a gravitational field pulling everything that way. You threw it out in the remote past, it jumped out and fell back in. It never crossed R equals 0. Well, I say it never crossed R. You say, sure, it crossed R equals 0. It crossed R equals 0 over here. But what Rindler time does that correspond to? This omega is called the Rindler time. It corresponds to omega equals minus infinity. So from the point of view of the accelerated reference frame, the observer sees the particle jump out at the very, very remote past, and then fall back in. Once it's fallen back in, can't see it anymore. But at what point in time does it fall back in over here? Omega time equals infinity. So from the perspective of this observer here, in his coordinate system, it never passes through the horizon over here. It just takes an infinite amount of omega time to see it pass through the origin, or to have it pass through the origin. In fact, an observer out here can never see it pass through here. Any observer looks back and sees the particle, no matter how late he looks back, he always sees the particle on the outside of the horizon. So what somebody outside sees when we drop a rock through the horizon, sees it just go slower and slower and slower and take an infinite amount of his time to pass through the horizon. Yeah?
What does the rock see?
Rock sees, if he looks out, nothing very special. He looks out, and he does see these hyperboloids, or these hyperbolas receding away from him all right. But he can see them. Well, let's see, sorry. Well, let's redraw the picture. Let's redraw the picture to make it a little bit clearer. I've got too many things on it already. Yeah. I drew that, yeah, I drew it the wrong way. Let's redraw it. Okay. So the rock goes through. Here's the hyperbola. Now, the rock cannot send a signal to the outside. Tries to send a signal to the outside, it will not go out. But it can receive signals from the outside. So this observer can send a signal that the falling rock will detect. Yeah, whatever. Yeah, in other words, this rock will have no difficulty seeing this observer. In fact, he will see him recede away from him. You know, the later, over here, he looks back, sees him moving practically with the same velocity. Over here, he looks back, and he sees him moving away. A little later time, looks back and sees him moving away a little bit faster. But as long as he lasts, he will look back and be able to see all of the observers on the outside, every single one of them. But the observers on the outside cannot receive signals from him. So he can absorb signals, detect signals, get information from the outside, but cannot send it back out. On the other hand, from the outside observers, the outside means the Rindler space here, from the outside observer's perspective, watching this rock fall, let's have him watch. I wish we had more colors. We've run out of colors. All right, so here's the observer. Let's get rid of some spurious lines. And how does he watch? How do you watch? You watch by collecting light signals from things. All right? Collecting light signals from the rock means looking back along a backward light-like direction, looks back and sees the rock over here. Goes a little further, sees the rock over here. Goes a little further, sees the rock over here. But keeping in mind that this hyperboloid here asymptotes to the light cone, as time goes to the very remote future for the accelerated observer, all he sees is the rock get closer and closer to the horizon, never passing it. Yeah?
This is so-called special relativity.
This is all special relativity, but in accelerated coordinate systems. Right. Now, what should we find about a gravitating mass? We should find something about a gravitational mass that looks like this. Yeah, and we will.
Paradoxical that the accelerated observer kind of appears is missing from a great bit of the history of the rock. I mean, until the rock actually passes the lower asymptote,
blue shifted.
he can't see the accelerated observer. The accelerated observer doesn't exist.
It's light signals from the past.
Yeah, but there's no accelerated observer in that past. But only when he crosses the...
Yeah, you are.
Only when he crosses...
So at some time, yes, so that's the sort of inverse of the other story. Right. So at some time, the rock suddenly sees from very, very far away, he sees the observer coming in.
It's created at that time, so it's
Effectively created at that time. And then sees him come in, start seeing him come in with a huge velocity. Coming in with a long velocity. If you really can see him, that would mean that this person was sending photons. If he was really sending photons and he was moving with close to the speed of light relative to the rock, of course he would be sending very, very blue shifted photons. Right. So he'd get a blast of radiation from here at this point. But when I... Okay. On the other hand, the observer out here sees the rock and sees radiation from the rock getting red shifted because he's moving away from the rock. So he sees what he sees is the rock moving slower and slower to the horizon, never quite getting there, and getting all of the signals progressively more and more redshifted. That's the nature of ripper space. What I'm not going to do is to write down Einstein's equations and solve them. It's a real mess. To write them down, we would first have to work out the curvature tensor, which means the Christoffel symbols, and then differentiate them, and then multiply them together, and then contract them to make the Einstein tensor. And it is a big, long mess. Somebody has done it for us. There are ways to do it which are more sophisticated and clever, where you can see what the answer is faster. But with the straightforward brute force methods, it is a big mess. And furthermore, there are a lot of Einstein equations. How many of them are there altogether? Well, d times d minus 1 over 2 or something. Well, they're not all independent, and so it's not really that bad. Really, there are only 2 independent ones that are important. But they're still quite unpleasant. What I'm going to do is to tell you the solution for a particular situation, and then analyze that solution, analyze the geometry that comes from it, which is far more fun than solving the equations. Now, what we're trying to do is put together something which is the analog of a point mass. Keep in mind that in Newtonian physics, the solution for a point mass has a degree of generality which goes beyond the point mass. If you have any spherically symmetric distribution of material, and you're outside the region that encompasses that material, then the standard Newtonian solution for the gravitational field is exactly the same as the point particle at the center. The same is true in general relativity. In Newtonian physics, I believe it's just called Newton's theorem. In general relativity, it's called Birkhoff's theorem, B-I-R-K-O-F-F, Birkhoff's theorem. What Birkhoff proved was that any spherically symmetric distribution of material, which is bounded outside the boundary of the material, the metric is exactly the same as the metric of a black hole. You could think of, to some extent, the metric of a black hole as being the analog of the metric of the point particle, although it is hardly point particle-ish in any ordinary sense of the word. Okay, so I'm simply going to write the answer down, and we'll look at it, and some pieces of it we'll recognize. We'll recognize everything about it, but some pieces will recognize why they are the way they are. Other pieces I will simply have to tell you. But before I do that, I want to write down flat space-time in polar coordinates. Now, not these polar coordinates. These are the polar coordinates of space. Not polar coordinates of space-time, but just ordinary polar coordinates of space. Let's just start with space. Now, we've written polar coordinates for space many times, but now I'm talking about 3-dimensional polar coordinates, not 2-dimensional polar coordinates. We have 3-dimensional space. Now, this is ordinary space now, not space-time. 3-dimensional ordinary space. And I want to describe it in polar coordinates. What does polar coordinates mean? What do polar coordinates mean? It means that you describe every point as being at a certain distance from the origin, r, having nothing to do with the r's that I might have written earlier over here. Doesn't have to do with this. Forget that. We're now concentrating on 3-dimensional space. Just put into your notes now that I have changed notation. Well, maybe I should call it capital R. Perhaps if I called it capital R, it might be less confusing. Let's call it capital R. Distance from the origin. No? Oh. Curvature. I think it's less, I don't think you're in too much danger of confusing a coordinate with a curvature, but you might confuse this coordinate with that one, so I won't call it what? P over 2? could call it P over 2. Let's call it R for radius. All right. It's really the radial distance from the origin. And not a single angle as you would have in 2 dimensions, but rather you think of a point on a sphere. A point on a unit sphere. Imagine a unit sphere. Begin with a unit sphere. A unit sphere means one of radius 1. So it's the Earth, except measured in units in which the Earth has radius 1. And it takes 2 angles to describe a point on the surface of a sphere. One of them, the polar angle, the other, the azimuthal angle. Which would you prefer to call phi? Phi is polar angle, all right. So that means an R and a phi and a theta. Now, first of all, let's think about the metric on a sphere. The metric of a sphere itself. Let's begin with the unit sphere. A unit sphere of radius 1, what is the metric on a unit sphere? Let's just call it ds squared. I'm not using d tau squared because I don't want to think of it as proper time. I want to think of it as spatial distance. ds squared. Anybody remember what it is? You said that phi was polar coordinate? All right, so it's d phi squared. And now what are we taking? Theta, we're imagining, is the angle from the equator or from the North Pole? We can either make, sorry, wait, that's this. This is, that's this, that. That's, are we taking this to be the angle from the equator or the angle from the equator? All right. Okay, so from the equator, North Pole. North Pole, angle from the North Pole. Okay, if it's angle from the North Pole, then we get sine squared theta d phi squared. And I'm not going to explain that. I'm going to let you work that out. That's the metric on a sphere. Okay? What's that? D theta squared. No. Wait, I'm sorry, what's the definition of the polar angle? Is it the angle from the pole? The angle from the pole. The angle from the pole. Okay, so from the angle, that's phi, right? We said that's phi. Yeah. So, sine squared phi. Good. Getting tired. I'm getting tired. Sine squared phi d theta squared. Sine squared phi. Good. Do I have it right? Yes. Good. All right. So here's the North Pole. Phi is measured relative to the North Pole, and theta is measured around the equator. This is the metric of a unit sphere. Now, supposing the sphere has radius r. What do we do with it? We just multiply it by r squared. Every length is r squared times, every squared length is r squared times bigger than it would be on the unit sphere. So it just becomes r squared times d phi squared plus sine of phi squared d theta squared. Did I get it wrong again? Yeah, not yet. This is the yeah, you're right. This is the metric on the sphere itself. All right, so that's the metric between points on a sphere of radius r. Now, what happens if I want to talk about points which are not on the same radius? Then I have to include here ds squared equals dr squared plus that. In other words, for points which are separated by radial distance, it's just dr squared. And that for points which are separated by angles, it's r squared times the metric on the unit sphere. There's another way to write this, which everybody usually, is common, is to write it ds squared is equal to dr squared plus r squared d omega squared. D omega squared is a shorthand for writing out the metric on the unit sphere. So d omega squared is a shorthand that's convenient if we don't want to keep writing thetas and phis. That's the metric of ordinary flat space in spherical polar coordinates. And remember now that omega stands for two directions, theta and phi. And the r squared here is just there because as you go further and further out, the sphere just gets bigger and bigger. That's all. Okay, that's now, what about space-time? Supposing we're doing flat space-time. This is the metric of space. It really is equal to just good old dx squared plus dy squared plus dz squared. That's all it is in some other coordinates, x, y, and z. But what about the metric of space-time? The metric of space-time, which is d tau squared, let's put it over here, d tau squared is equal to, let's call it dt squared, minus dx squared minus dy squared minus dz squared. Right? That's, where do the c's go if we wanted to put speeds of light in? I think they would go over here. If we wanted to put speeds of light in, they would go over there. I'll include them a little bit for the moment. How do we rewrite that in the polar coordinates? Well, we just rewrite it as d tau squared equals dt squared minus exactly what we see here. dr squared plus r squared d minus r squared d omega squared. And I'm not going to, if I wanted to put the speeds of light in, they would go in here in the denominator. dt squared minus dr squared minus r squared d omega squared. That's the metric of absolutely flat space-time, just using spherical polar coordinates. The Schwarzschild metric, being the metric of a spherical distribution of mass, is conveniently described in spherical coordinates like this. When you have a problem with the symmetry of a sphere, it's always convenient to use polar coordinates. Right? If you use polar coordinates, then I'm now going to write down the metric, and I'll tell you what goes into it. This is the solution. It's a solution of Einstein's equations with any spherically symmetric, let's say, energy distribution, or T naught naught, with any spherically symmetric distribution of energy and of energy, right? Outside the boundaries of that region. So here's the region, and we look outside the region. The general solution outside the region has the following form. D tau squared equals 1. You know what? Before I do this, let me remind you about the Newtonian solution. The Newtonian solution, of course, is in terms of a gravitational potential. Now we're going to get into trouble. Gravitational potential is called phi.
Because it's like an angle.
It's not like an angle. Gravitational potential is capital phi. Right. Gravitational potential is gravitational phi. And what's the solution of Newton's equations for a point mass? It's just phi equals the mass of the gravitating object, g divided by r, with a minus sign or a plus sign, I can't remember, minus sign, right? Right? Minus sign. That's because it's attractive. It pulls you towards the origin. Okay, now remember what the connection between g naught naught and phi is. G naught naught, at least approximately, is equal to a constant, let's write it out, is equal to some constant. When I say constant, it's a piece which doesn't have a derivative. And then the piece which has the derivative is supposed to be plus, is it phi over 2? Or is it 2 phi? 2 phi. 2 phi, my mistake. 2 phi. That was the connection that we discovered several times in discussing motion of particles, that the motion of a particle connects g naught, or in relativistic theory, g naught naught replaces phi, or at least its derivatives do. There's a factor of 2 there and an additive constant, which doesn't matter when you differentiate it. Okay, that's g naught naught. So we would like now to write the metric. We'll start with some dt squared. It's the thing which replaces the coefficient 1 over here. Flat space-time has a coefficient 1. Let's see what it has to have. It's going to be g naught naught, and what I expect is it will have the form some constant plus twice phi, period. But phi is just minus mg over r. Now that may or may not be exact. Happens that it is exact. Minus, there's a factor of 2, and so it's minus 2mg over r. Now what shall I take this constant c to be? Well, let's go very, very far from the black hole. This is a black hole of stellar mass. We go 75 billion trillion zillion light years away from it. We don't see it, right? I mean, it's a negligible perturbation on our geometry. And our geometry originally was just dt squared with a 1. There's only one thing this could be. It's got to be 1. Very far from the black hole, when r is extremely large, this is negligible. When r is extremely big, and we have to go over to what would be just flat space, so it's got to be 1. This term here is unaffected. This is the angular part on the sphere. It turns out, when you work out the equations, turns out no effect on it, just exactly the same. So minus r squared d omega squared. And this term is also slightly affected in a manner similar to this one. This is the hard part. This is actually not so hard to show that this one's unaffected. This one was easy. We just used the correspondence between g naught naught and 2 phi. The hard one, which requires the extra labor of solving Einstein's equations, is this. 1 divided by 1 minus 2mg over r, dr squared. Now again, when you go far away from the black hole, or from the, it doesn't have to be a black hole, when you go far away from the mass, r becomes large, 2mg over r becomes small, 1 just stays there, and this just becomes 1. So it goes right over to this formula here, but there are 2 corrections, one in the dt squared and one in the dr squared. They're identical, except one occurs in the denominator and one occurs in the numerator. That is not an accident, but it's not something I can easily explain without spending some time going through the equations. But it's good enough. We don't really need to. This is a nice structure. Let's see, if I put the speeds of light in, let's see if we can figure out where they would go. Let's figure out what the units of capital G are. All right, so let's figure out what the units of capital G are. Force is equal to mass squared G over R, right? No, energy. Energy is mass squared G over R. I don't literally mean equals, although I mean the same units, okay? So what's the energy? What's the units of energy? Units of energy are mass times velocity squared. Let's use c squared. As units of mass times velocity squared, where c has units of velocity because it's the speed of light. And that's got to equal m squared g over r. So we cancel out a m. We divide by this m over here, and we multiply by r. So whatever g is, it has units of length, velocity squared divided by m. Did I get it wrong? Oh, okay. I think I got it right. I'll just call this r, capital R. All right. Now, twice mg over r, it has to have the same dimensions as 1, because you can't add something with different dimensions to something else. But it doesn't. If I work out, let's see what we have. From this equation over here, I can see that mg over r has units of the speed of light squared. I need a c squared in the denominator. Yeah, no, we don't want to put the c squared here because we want to match on to flat space-time. Okay? So we don't want to put the c squared there. All right. Now, that same c squared has to go over here. But let's put back our c squared, our original c squared here. There's a c squared here. That means there's another c squared downstairs here. If I put back all the c squares, I believe it would look like that. That's what it would look like. Right. Notice that the speed of light down in here makes this very, very small. So it's a very small perturbation on the metric. This is characteristic. Don't expect that an ordinary mass like the sun is going to make tremendously big perturbations on the structure of the metric. It won't. Space is not highly deformed near the sun, even though the sun has a large mass. And there's a significant gravitational potential of the sun, but it doesn't translate into a large deformation because of the c squared downstairs. All right, so the c squared is what keeps the geometry around the sun from looking highly curved. All right, so that's the Schwarzschild metric. This is the whole metric of a black hole, and it's the simplest of black holes. It's not rotating. It doesn't have any electric charge. But it has all the basic features that we're going to explore. The next time, what I'm going to show you is how similar this metric, it doesn't look anything like it, but how similar the metric of the black hole is to the metric of Rindler space. Let me just write it down for you again. R squared d omega squared minus d r squared. Well, it's a different r. R squared d omega squared minus d r squared. That was minus dx squared minus dy squared, minus dz squared minus dy squared. All right. Looks very, very different. Doesn't look anything like it. We're going to find out that the horizon of the black hole is very, very similar to the horizon of the Rindler space. And that's going to be our goal. That really will carry us through the quarter. So, as I said, our main goal is going to be to understand the horizon of this black hole. From this point of view, you can't even see that it has a horizon. Any questions before we leave? No?
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.
Very well. I've arrived at my objective opinion. This is one of the most amateurish, hackneyed, odious pieces of effluvium ever to wash down the pike.